So let's solve the exercise problems of dual nature of radiation and matter. These are some important formulas and constant values that you need to know before solving the sums. You can take a screenshot of it if you want. Let's see the first question. What will be the energy of each photon in monochromatic light of frequency 5 into 10 raised to 14 hertz? So you need to find out the energy of photon. Energy of photon is given by E equal to h nu. Okay, so we have been given the value of frequency, and we know that Planck's constant is 6.63 into 10 raised to minus 34 joules second into into frequency of light, that is 5 into 10 raised to 14 hertz. So solving this we get 3.315 into 10 raised to minus 19 joules. So this is the value of energy of each photon in monochromatic light of frequency 5 into 10 raised to 14 hertz. So in terms of electron volt, you just need to divide this value by 1.6 into 10 raised to minus 19. That will give us 3.315 into 10 raised to minus 19 by 1.6 into 10 raised to minus 19, and here electron volt will come. That will give us the value 2.07 electron volt. So this was the solution of first sum. Let's move to second sum. Observations from an experiment on photoelectric effect for a stopping potential by varying the incident frequency were plotted. The slope of the linear curve was found to be approximately 4.1 into 10 raised to minus 15 volts second. Given that the charge of an electron is 1.6 into 10 raised to minus 19 coulomb, find the value of Planck's constant h. So an experiment was conducted and a graph was plotted against stopping potential versus incident frequency, and it was a linear curve, and the slope is given as 4.1 into 10 raised to minus 15 volt second. Okay, what we need to find out is Planck's constant value. So yeah, in this sum we'll experimentally, means from the given experimental data, we'll find the value of Planck's constant. So we already know the value of Planck's constant is 6.63 into 10 raised to minus 34 joules second. But what this experiment gives us the value, let's see that. So according to Einstein's photoelectric equation, h nu equal to work function plus Ke max. Okay, we all know that Ke max is equal to E V naught. V naught is the stopping potential. Also, work function in terms of threshold frequency is given as h nu naught. So substituting this value, we arrive at an equation E V naught equal to h v minus V naught. So V naught will be equal to h by E nu minus nu naught. Now in terms of wavelength, what we get is, to write it more precisely, we can say V naught equal to h by E nu minus h by E nu naught. Now this equation is analogous to our straight line equation y equal to mx plus c, where m gives us the slope of our line. On a same analogy, we can say that our slope is equal to h by E. It is h by E. We know the charge of electron, this value. We know the value of slope, this. We can determine the value of h. So let's do that. Slope is given as 4.1 into 10 raised to minus 15 volt second by h upon 1.6 into 10 raised to minus 19 coulomb. So this implies our h will be equal to 4.1 into 10 raised to minus 15 into 1.6 into 10 raised to minus 19. Solving this we get as 6.56 into 10 raised to minus 34 joule second. Now I know this value is not exactly the value we know of H, but this was an experiment data and there might be some errors. Let's see the third sum. The threshold wavelength of tungsten is given as 2.76 into 10 raised to minus 5 centimeter. So we have threshold wavelength, that is 2.76 into 10 raised to minus 5 centimeter. So we need to convert it into meter. So that will become 2.76 into 10 raised to minus 7 meter. First part of the question wants us that explain why no photoelectrons are emitted when the wavelength is more than 2.76 into 10 raised to minus 5 centimeter. So as we all know, photons are emitted when when the energy of photons are above some threshold frequency, or it surpasses the work function value, which is h nu naught or h c by lambda naught. So as we know, h by c is constant. From this we can say that work function is inversely proportional to lambda naught, and by increasing the lambda naught, our work function will decrease. So as we know, the material is the same, we are not changing the material. So by increasing the value of wavelength, we make sure that no more electrons will be emitted. So second part of the questions want us to know what will be the value of maximum kinetic energy of electron ejected in each of the following cases. So first case is they have given the radiation of wavelength 1.8 into 10 raised to minus 5 centimeter. So lambda is given to us as 1.8 into 10 raised to minus, so let's write it as 10 raised to minus 7 meter, and we need to find out Ke max. So from Einstein photoelectric equation, Ke max will be equal to h nu minus work function, right? So hc by lambda minus work function is hc by lambda naught. So taking hc common, we get 1 by lambda minus 1 by lambda naught. So the value of h is 6.63 into 10 raised to minus 34 joule second, and c is 3 into 10 raised to 8. So solving this both, we get 1.989 into 10 raised to minus 25 upon 1 by lambda. Lambda is 1.8 into 10 raised to minus 7. So minus 7 will go up, 10 raised to 7 divided by 1.8 minus threshold wavelength is 2.76 into 10 raised to minus 5 here. So same thing, 10 raised to 7 divided by 2.76. So solving further, Ke max can be written as 1.989 into 10 raised to minus 25 into 10 raised to 7. I have taken 10 raised to 7 outside. 1 divided by 1 by 8 minus 1 divided by 2.76. This will give us 19.89 into 10 raised to minus 19 into 0.555 minus 0.362, which can be further simplified as 3.83 into 10 raised to minus 19. This is minus. So the value of Ke max in terms of electron volt can be given as, by dividing it with 1.6 into 10 raised to minus 19, as 2.40 electron volt. Now the second part of the sub question is radiation of frequency 4 into 10 raised to 15 hertz is made incident on the tungsten surface, and we need to find out the maximum kinetic energy. So let's do that. So for the second part, radiation is in terms of frequency is given to us. So let me just write 4 into 10 raised to 15 hertz. So from Einstein photoelectric equation, Ke max will be equal to h nu minus work function. So h nu. Now I'll not change this thing in terms of wavelength, because we have already given the value in terms of frequency. So 6.63 into 10 raised to minus 34 into 4 into 10 raised to 15 minus. Now work function, we need to write it in terms of wavelength only, because is given in terms of wavelength only. So hc by lambda. So this term becomes 26.52 into 10 raised to minus 19 minus, by solving this was lambda naught. HCV no 19.89 into 10 raised to minus 26 by lambda naught is 2.76 into 10 raised to minus 7. So solving this we get 26.52 minus 7.2 into 10 raised to minus 19, which will give us 19.32 into 10 raised to minus 19 joules, Ke max value. Now in terms of electron volt, if you want, Ke max will become 12.075 electron volt. Let's see the next one. Photocurrent recorded in a microammeter in an experiment setup of photoelectric effect vanishes when the retarding potential is more than 0.8 volt. That is, we have been given retarded potential V naught will, that is 0.8 volt of incident radiation if the wavelength of incident radiation is 4950 Armstrong. That is, lambda is given as 4950 Armstrong. We know Armstrong is 10 raised to minus 10 meter. So I can directly write it 4.95 into 10 raised to minus 7 meters. If the source of incident radiation is changed, the stopping potential turns out to be 1.2 volts. Initially it was 0.8 volt. Find the work function of the cathode material and the wavelength of the second source. So first let's find the work function from Einstein photoelectric equation. Work function can be written as h nu minus Ke max. The values given to us are in wavelength, so let's write them in hc by lambda minus Ke max is E V naught. So hc, we know the value 19.89 into 10 raised to minus 26 divided by lambda is 4.95 into 10 raised to minus 7 minus E 1.6 into 10 raised to minus 19 V naught is given as 0.8. So we get 4.018 into 10 raised to minus 19 minus 1.28 into 10 raised to minus 19. So solving this we get 2.738 into 10 raised to minus 19. This is the value of our work function in terms of joule. Now in terms of electron volt, we will get 1.71 electron volt by dividing it with 1.6 into 10 raised to minus 19. So now our stopping potential is 1.2 volts. We already know the value of our work function. So hc by lambda, I'm directly writing the Einstein photoelectric equation in terms of wavelength, which will be equal to EV naught plus work function. So we need to find out the value of this wavelength for the given second source. So HC we know 19.89 into 10 raised to minus 26 divided by lambda. EV naught 1.6 into 10 raised to minus 19. V naught is 1.2. Work function what we previously found out was 2.738 into 10 raised to minus 19. Here the work function is same because we are not changing the material. The thing is the metal from which electrons are emitting is the same, just we are changing the source from which the photons are emitted. So the work function for this thing will remain same. So solving this we get 19.89 into 10 raised to minus 26 divided by lambda equal to 4.658 into 10 raised to 10 10 raised to minus 19, which implies lambda will be equal to 19.89 into 10 raised to minus 26 divided by 4.658 into 10 raised to minus 19. I would advise you all to use the logbook for doing these calculations. So solving this we get 4.305 into 10 raised to minus 7 meter, or we can write this 4305 Armstrong. Let's look at the next sum. Radiation of wavelength 4500 Armstrong is incident on a metal having work function 2 electron volt. Due to the presence of a magnetic field, the most energetic photoelectrons emitted in a direction perpendicular to the field move around in a circular path of radius 20 centimeter. What is the value of magnetic field? So here we have been given the radiation wavelength lambda, that is 4500 Armstrong, which can be written as 4.5 into 10 raised to minus 7 meters. Work function is also given 2 electron volt, which we need to convert it into joules by multiplying it with 1.6 into 10 raised to minus 19. That will give us 3.2 into 10 raised to minus 19 joules. Also the radius of the circular projection of electron is given as 20 centimeter, which can be written in meters as 0.2 meters. So first let's find out the kinetic energy. Ke max is equal to h nu minus work function, which can be written as hc by lambda minus work function. Solving this, 19.89 into 10 raised to minus 26 divided by 4.5 into 10 raised to minus 7, minus work function is 3.2 into 10 raised to minus 19. So solving this we get kinetic energy as 1.22 into 10 raised to minus 19. This values is in terms of joules. Now as we all know, for the electron moving in a circular path, the centripetal force is equal to QVB. So V cancel, we get mv by r equal to qb, and we need to find out the magnetic field. So B will be mv by qr. Q is nothing but charge of electron, that is 1.6 into 10 raised to minus 19. So mv can be written as momentum qr. So we know kinetic energy in terms of momentum can be given as sorry, momentum in terms of kinetic energy is given as 2m ke. So right, solving this, our magnetic field 2m ke by q r. So let's put all the values in, solve it. So our magnetic field B becomes 2 into 9.1 into 10 raised to minus 31. This is mass of electron into the kinetic energy, which we got as 1.22 into 10 raised to minus 19 divided by charge of electron 1.6 into 10 raised to minus 19 into radius was 0.2 meter. So solving this, we get magnetic field as 1.47 into 10 raised to minus 5 Tesla. I hope you understand this sum.